students, this is Rita, Assistant Professor of Physics from Government College for Girls, Bodia Kheda, Fatehpur. In my this video of unit polarization, I will discuss the topics production and detection of circularly and elliptically polarized light and the retardation plates. So first of all, we will discuss circular and elliptical polarized lights, how we can produce them and how we can detect them. So elliptically and circularly polarized lights, they are nothing but they are produced because of the interference of polarized lights. You know very well that when unpolarized light incident normally on a thin plate of any uniaxial crystal whose phase cut parallel to the optic axis, then ordinary and extraordinary rays both travel along the same path but with the different velocities. Similarly, if we use a beam of plain polarized light as shown in the figure here and it is made to fall normally on such a crystal, then what happens? It will also split up into ordinary and extraordinary component and they will travel through the crystal in the same direction but with the different velocities according to Huygens principle. So that's why we will get the two wavefronts. For O wavefront we have the spherical shape and for the E wavefront we have the ellipsoid shape. You know it very well. Now if we use a light which is of monochromatic nature, means having a wavelength lambda and amplitude A, if it is incident on this uniaxial crystal, then what happens that in that case we say that this has the linear vibration along the direction OP. You can see in the figure number B here that the incident light has the vibration along the direction OP, which is making an angle theta with the optic axis, with the x-axis here. Then what happens that on entering the crystal, it will definitely split up into the two components, that is ordinary component and the extraordinary component. The ordinary component will have the vibrations along the direction y, that is along OY, and it is represented by A sin theta. And the extraordinary component will have the vibrations along OX and it will be shown by A cos theta. A cos theta will be its amplitude. So the amplitude of O ray is A sin theta and of E ray is A cos theta. Right. So according to Huygens double refraction, we can say that both the component will travel in the same direction, which is perpendicular to the plane of paper, but it will travel with the different speeds, different velocities, and that will definitely depend upon the nature of crystal. You know that in the calcite crystal, which is a negative crystal, E ray travels faster than O ray. Okay, so we should know this thing that because of unequal velocities of these two components, although on entering in the crystal they have the same phase, but because their velocities are different, so on emergence their phases will be different, and as the two rays will have a path difference, because of this phase difference they will have the path difference, and that will depend upon the thickness of the crystal. So we can say that the emergent light will therefore consist of two simple harmonic vibrations in two mutually perpendicular planes. Okay, so they can be combined together in order to produce a single motion which could be linear, circular, elliptical, and that will definitely depend upon the phase difference between the two components and the magnitude of angle theta. So we can say that circular elliptical polarizations are nothing but they are the examples of interference of polarized light. So if we want to know about the formula that how we can theoretically find out a relationship for this particular case, then we can do it like this, that if we say that there is a phase difference between the two components after traveling a certain thickness in the crystal, and this phase difference is represented by delta, then we can write down the displacement equations for E ray as well as for O ray. For E ray I can write down x is equals to A cos theta, its magnitude, its amplitude, and sine omega t plus delta. And for O ray we can write down y is equal to A sin theta, which is the amplitude, and along with this I can write down sine omega t. These are the displacement equations. If I substitute A cos theta as small a and A sin theta as small b and we replace them, then we will get this x and y. So x will be is equal to a sine omega t plus delta and y is equal to b sine omega t. Now if we rearrange these equations as x by a and y by b we get here, then if we solve them by using the general relations, then we will get a general equation of ellipse as shown here in the box, that x square by a square plus y square by b square minus 2xy by ab cos delta equals to sine square delta. So this is the general equation which we have obtained, and this is the equation of ellipse. So we can say that light which is emerging from the crystal plate is generally elliptically polarized. Now we can here discuss some special cases. Okay, so we have already said that the phase difference between E and O component depends upon the thickness of the crystal covered. So we discuss the special cases. That first case is if thickness is such that the phase difference is equal to 0 or it is 2n pi. In this case sine delta will be 0 and cos delta will be 1. So in substituting in the previous relation, we will get y is equal to plus minus b by a x, which means that we get a straight line which is passing through the origin and it is having the slope b by a. So the emergent beam will be plane polarized, and we can say that in this case the crystal plate will be called as a full wave plate, right? So if the thickness of the crystal is such that delta is equals to, that is the phase difference between the E and O component is pi or 2n plus 1 pi, then we can say that sine delta will be 0 and cos delta will be minus 1. By substituting these values, we will get y is equal to minus b by a x, which means that again we get an equation of the straight line which is passing through the origin, but now it is having the slope minus b by a. So the emergent beam will be again polarized, plane polarized in this case also, okay, but with a different slope, right? So we can say that the crystal plate will be called as half wave plate. Okay, now the next case is that if the thickness is such that the phase difference is pi by 2 or 2n plus 1 pi by 2, in that case sine delta will be 1 and cos delta will be 0. And if we say that a is not equal to b and theta is not equal to 45 degree, for this particular case we get the equation x square by a square plus y square by b square equals to 1. You know very well that this is the equation of ellipse with the axis along x and y direction. So we can say that the emergent beam in this case will be elliptically polarized, and the plate is known as to be quarter wave plate. Okay, so however, if in this particular case, if we put a equals to b and theta is equal to 45 degree, then this equation will reduces to x square plus y square is equals to a square. So which is the equation of a circle which is having the radius a. So we can say that the emergent beam will be the circularly polarized in this particular case. So we have seen that the plane polarized and circularly polarized lights are nothing but they are the special cases of elliptically polarized light. You must keep this thing in your mind. Next case is if the thickness of the crystal is such that delta is equals to pi by 4, then in that case sine delta and cos delta both will come out to be 1 by square root of 2. So by substituting in the previous equation we get this relation. You can see here. So this is nothing but this is the equation of ellipse with the major axis inclined in the positive direction of x-axis. So we can say that emergent beam will be the elliptically polarized light. Okay, so in the figure also you can see here that the elliptically polarized light could produce the plane polarized and the circularly polarized, means both are the special cases of elliptically polarized light. We can see here that if phi is equals to 0 we get the plane polarized, if phi is equal to pi by 2 then we get the circularly polarized, and for phi is equal to pi by 4 we get the elliptically polarized light, right? So here I have shown that elliptical polarization is the most general form. Linear and circular cases are the special form of elliptical polarization, as I have already told you. So here we can also talk about the handedness of the elliptical polarization. We get the two type of elliptically polarized light, that is the right-handed and the left-handed polarized lights. We can discuss it here like this. in order to discuss the handedness, which is nothing but that is the sense of revolution of elliptical polarization. So we can say that if the electric vector E revolves counterclockwise, then the polarization is said to be left-handed. And if the electric vector E revolves clockwise, then the polarization is said to be right-handed. Okay, you can see in the pictures here shown here, we can define the different cases for the different phases. You can see that for delta, which is equals to which is lying between 0 to pi. If delta is lying between 0 and pi, then we can say that the elliptical vibration is described counterclockwise. Okay, then it is said to be left-handed elliptically polarized. And for the delta which is lying between pi and 2 pi, then the ellipse is described in the clockwise direction and the light is said to be right-handed elliptically polarized. You can see in the figure here also. Then the cases for the circular polarization, we can say that if delta is equals to pi by 2 or it is 3 pi by 2, then the ellipse will change into the circle. You can see here the figure for pi by 2 and minus pi by 2, I have shown as the circular polarized light. Then for delta is equal to 0 or delta is equals to 2 pi, then the plane of vibrations are parallel and we can say that light is said to be the plane polarized or the linearly polarized in this particular case. So this was all about the elliptically and the circularly polarized lights. The next, and which is very important topic, is the phase retardation plates. What are phase retardation plates? These are nothing but these are the plates which are able to produce a particular phase difference between the ordinary and the extraordinary component. So we can say that a doubly refracting uniaxial crystal plate of uniform thickness which is having its refracting surface parallel to the direction of optic axis, and it is capable of producing a definite phase difference between the O and E component, and then this plate will be known as the phase retardation plate. You can also explain it like this: a retardation plate is an optically transparent material which resolves a beam of polarized light into two orthogonal components, retards the phase of one component as compared to other, and then recombine the components into a single beam with the new polarization characteristics. So these are the retardation plates. We will talk here about the two retardation plates. The first one is the quarter wave plate. What is a quarter wave plate? It is a uniaxial doubly refracting crystal plate cut with its optic axis parallel to the refracting phases and having the thickness so that it can produce a phase difference of pi by 2. If I say that phase difference of pi by 2, it means the path difference of lambda by 4 between the O component and E component. Then this particular plate will be known as quarter wave plate. Okay. So if I say that a beam of plane polarized light having the wavelength lambda is incident normally on such a plate, then it is broken up into two components, E component and O component. Okay. So what we say that then both these components will move, but they will move with the different velocities. Okay. So we can see here that if we talk about the positive crystal, then refractive index of extraordinary ray will be greater than that of ordinary ray. So it means that ordinary component will travel faster in the positive crystal and extraordinary component will travel faster in the negative crystal. Right. So I can say that the distance covered by the ordinary component will be mu ed, and that is by the ordinary component is mu naught d, and for extraordinary component it is mu e d. Now if we put the values here, then I can write down for a positive crystal mu e minus mu o outside d is equals to lambda by 4. So from here I can get the value of d, that is the thickness of plate, in order to produce the path difference of lambda by 4. Okay. So what are the uses of quarter wave plate? A quarter wave plate can convert the plane polarized to a circular polarized or the elliptical polarized light, and vice versa we can do. Right. So this was the quarter wave plate. The next one is the half wave plate. Half wave plate is nothing but it is a doubly refracting uniaxial crystal plate which is having the refracting faces parallel to the direction of optic axis and having a thickness such that it can create a path difference of lambda by 2 or phase difference of pi. Okay, then we can say that it is a half wave plate. So in the similar way as we have done in the quarter wave plate, we can say that thickness of half wave plate will be T equals to lambda by 2 mu E minus mu O. Okay. So this will be the case for positive crystal. For negative crystal, we will write down mu O minus mu E, right, in the denominator. Because for the positive crystal, O ray travels faster, and for the negative crystal E ray travels faster. Okay, so this was about the half wave plate. You can derive a relation as I have already told you that we can write down mu E minus mu O T equals to lambda by 2. The path difference between 2 will be equal to lambda by 2 and the phase difference will be pi. So what is the use of half wave plate? Half wave plate can convert the right circular polarized to a right elliptical polarized light, or left circular polarized to left elliptical polarized light, and vice versa. It can be done. Okay, you can see in the figure also here that when a linearly polarized light is passed through a half wave plate, then transmitted light is also linearly polarized. And if the plane of polarization of incident light makes an angle theta with the direction of optic axis, then plane of polarization of transmitted beam makes an angle of minus theta with the same direction. You can see in the figure I have shown by the red arrows incident and the transmitted. You can see incident is making an angle theta and transmitted is making an angle minus theta. So we can say that the plate has effectively rotated the angle by 2 theta. Okay, so that is why these type of plates are used in polarimeters as a half shade device. Okay, so this was the use of the half wave plate. Now the uses of half wave plate and the quarter wave plate are that quarter wave plate is used for producing elliptically and circularly polarized light, and it is used for analyzing all kind of polarized lights. And half wave plate is used as the half shade device in the polarimeters. One thing is to be noted here that the thickness of quarter and wave plate, a half wave plate, depends upon lambda. So these two plates can be used for one particular color and not for all the colors, right? The next topic is production of elliptically polarized light. How we can produce the elliptically polarized light. So for this particular case, we have to use the unpolarized light, and if we made it incident on the Nicol prism, it will get splitted up into two components, and Nicol prism will produce the polarized light. And if this polarized light is made to incident on the quarter wave plate such that the angle made with the optic axis is other than 0, 45 or 90 degree, then the emergent light from the quarter wave plate will be elliptically polarized light, right? So for this particular case, we have to make sure that the angle theta should be other than the 0, 45 degree or 90 degree in order to get the elliptically polarized light. How we can produce the circularly polarized light? You can see here in the figure that when the unpolarized light is made to incident on the polarizing Nicol prism, then we will get the plane polarized light out of it, and this plane polarized light is made to incident on the quarter wave plate at an angle of 45 degree. When it will pass through it, we will get the circularly polarized light, right? So we can also analyze it using the different Nicol in the crossed position. Okay, so this is how we can produce the circularly polarized light. Next is how we can detect the plane polarized and the circularly polarized light. It's very simple that in order to detect the plane polarized light, first it is made to pass through a Nicol prism. Okay, and when the direction of its vibration is parallel to the principal section of Nicol, the beam will obviously pass through it. and if the direction of vibration of incident beam perpendicular to principal section of Nicole, beam will be cut off by TIR, that is total internal reflection. So as the Nicole is rotated, there will be an extinction of light twice in each rotation of the analyzing Nicole. So we can say that if the intensity of light varies with zero minimum twice in each rotation of the analyzing Nicole, then the light is plane polarized light. That is, we should get minima 2 times in the case of rotation, 2-time rotation. Right? So this is how we can detect the plane polarized light. Next is the detection of circularly polarized light. If we pass the beam of circularly polarized light through a Nicole prism, it will be divided into O component and the E component. And on emergence, the amplitude of transmitted beam is same for all the positions of Nicole. However, circularly polarized light gives the same effect as the unpolarized light. So these two components cannot be distinguished by the Nicole prism alone. The next is how we can distinguish between the quarter wave plate, half wave plate and the ordinary glass plate. In order to differentiate between these three, what we do, we use a monochromatic source of light which will produce the unpolarized light, and if this unpolarized light is made to pass through a Nicole prism which is N1 here, also known as polarizer, it will produce the PPL, that is plane polarized light. And when this plane polarized light is made to pass through a plate which is to be verified that whether it is quarter wave plate, half wave plate or glass plate, we put this plate in the path of plane polarized light and then we analyze it with the help of the second Nicole prism which is N2 here, and depending upon the output what we are getting here, we can say that which type of plate here which we have inserted. So this is the way how we can distinguish between these three type of plates. So that's it. Thank you for this particular video.